All right, let's just jump right into this explainer. If you're an electrical engineering student, or maybe a fresh grad getting ready to step into that high-pressure interview room, you know you're going to face questions that test way more than just your textbook memory. They want to see your practical, conceptual grasp of industrial components. So today, we're building the absolutely perfect, bulletproof answer to one of the most common and honestly most frequently fumbled questions out there. What exactly is the role of the IGBT inside a variable frequency drive? We're going to break this down so you don't just memorize some robotic answer, but actually understand the mechanics under the hood. Here's our roadmap for this explainer. We'll start with the core question, look at how we actually control motor RPM, dive into the high-speed switching of the IGBT, tackle the inevitable PWM follow-up questions, and finally wrap it all up with an analogy that'll seriously impress any interviewer. So let's set the scene in that interview room. The interviewer leans across the desk and asks, what is the basic role of an IGBT in a VFD? Or maybe they phrase it like, why is this one specific component so incredibly crucial to the drive? Now, when you hear this, you've got to resist the urge to immediately spout out a bunch of technical jargon about transistors. Seriously, hold back for a second. You need to set the stage by looking at the macro level first. Show them you understand the why before you dive into the how. To do that, we first have to talk about why we even need to control motor speed in the first place. Think about it. If you connect an AC induction motor using a standard direct online or DOL starter, you are completely locked in. The motor spins at its fixed RPM, and you literally have no option to vary that speed. But out in the real world, industrial processes are dynamic. You've got massive water pumps trying to maintain exact pressure in a city grid, or a delicate conveyor belt in a bottling plant. You definitely don't always want maximum speed. A VFD gives you the superpower to manipulate the motor's RPM, totally customizing the speed based on the exact real-time requirements of whatever load you're driving. Let's put some real numbers to it. Say you've got a motor running at 1500 RPM, but then suddenly the system demand drops. Maybe that bottling conveyor belt needs to slow down for a quality inspection phase, and you need that motor to drop down to exactly 1200 RPM. The VFD is the entire reason that precise variation is even possible. But hey, the interviewer's question was about the IGBT, right? So who's actually doing the heavy lifting at the micro level to force that speed change? Well, let's look at how the VFD is built. Inside, you've got three main stages. First, we take our standard three-phase AC supply input. Next, that power passes through the rectifier stage, which converts that alternating current into direct current, or DC. And finally, we hit the inverter stage. This is where that DC gets converted back into a highly controlled AC output to feed the motor. And it is right here, in this third stage, where our star player lives. Enter the IGBT. The secret sauce here is sheer speed. The IGBT, which, by the way, stands for Insulated Gate Bipolar Transistor, is a power electronic device sitting right there in the inverter section. And its primary job? High-speed switching. And when I say high speed, I mean it is literally executing thousands of on and off operations every single second. It's this rapid-fire switching that sculpts the exact voltage and frequency being sent to the motor. The IGBT is the fundamental component dictating that RPM. So when you drop the speed from 1500 to 1200, the IGBT's switching pattern is exactly what made that happen. Now, if you've got a good interviewer, they aren't going to stop there. You've got to be prepped for the inevitable cross question. They're going to say, okay, sure, it acts as a switch, but exactly how does turning on and off thousands of times a second actually vary the motor's RPM? This is the pivot. They're testing the depth of your knowledge. And they might even throw in some common follow-up questions here too, like how does the VFD handle the harmonic distortion generated by all this switching? Or what impact does this have on motor heating? To answer all of these, you need to firmly pivot from the what to the how. And your golden answer is PWM, pulse width modulation. By modulating, or basically changing the width of the electrical pulses as it switches that DC voltage on and off, the IGBT can precisely control the average voltage and the average frequency delivered to the motor. It's pretty elegant, really. Wide pulses mean a higher average voltage, narrow pulses mean lower. This is exactly how we manage speed, and dealing with the resulting harmonics is a huge part of drive design. But to truly show you know your stuff, you absolutely must point out one final crucial detail. A VFD using PWM does not output a pure sine wave. And this leads us to the ultimate way to close out your answer. You want to first establish the fundamental problem for the interviewer. An AC induction motor is inherently designed to operate on a pure, perfectly smooth alternating current sine wave. That's what it wants to run smoothly, keep cool, and operate efficiently. But the reality of what the VFD is spitting out is completely different because the IGBT is a switch. It's strictly either on or off. It can't create a smooth curve. It continuously triggers these highly rapid, blocky square pulses. If you look at the raw voltage output of a VFD on an oscilloscope, it looks harsh, jagged, and honestly, kind of messy. So how on earth does a motor that craves a smooth wave operate on these harsh square pulses? This is exactly where you drop a killer analogy. Explain to the interviewer that it's basically an electrical illusion. Imagine you have hundreds of tiny, rigid square tiles, and you arrange them really tightly in a circular pattern. Up close, yeah, it's just a bunch of sharp corners. But if you step back 20 feet, the human eye is fooled into seeing a perfectly smooth circle. Our electrical system is doing the exact same thing. The VFD's rapid square pulses are fired so incredibly fast, and the motor's own inductive properties naturally act as a filter, that the motor is effectively tricked. It sees a generalized average sine wave. It acts exactly as if it's receiving a smooth AC curve, which is what allows it to run so seamlessly at that customized RPM.
When you frame your answer this way, starting with the real-world industrial need, explaining the IGBT switching speed, nailing the PWARM concept, and finishing with that square circle illusion, you leave absolutely no doubt that you understand this technology inside and out. And as we wrap up this explainer, it leaves us with a pretty fascinating thought. If something as massive and powerful as an industrial motor relies entirely on perfectly timed microsecond illusions just to function, what other realities in our modern electrical systems are just high-speed tricks of the trade? Definitely something to think about next time you hear a massive machine spooling up. Thanks for joining me on this explainer. Keep learning, keep questioning, and go nail that interview.